One of the things that I wanted to talk about that I feel like I really haven't, I mean, I stressed it, but I haven't really gotten down to explaining is Les Chataliers principle for both aldehyde and ketone reactions that exist to form as hydrates or gendiols, and the formation of acetals. And if you look at these, you'll see kind of some common similarities between the two. I'm going to go ahead and just use hydrates and acetals, but the thing is, these are equilibrating reactions. So let's just draw out a generalized mechanism for either one of these, because what is the first step? It's pretty much the same. So you have your carbonyl carbon there, some type of a acid comes in, and I'll just use the hydrate, I guess, to exemplify this example a little bit more so. But the strongest acid you can get in water is a hydronium ion. That hydronium ion is going to protonate one of the lone pairs of the ketone or a aldehyde. And then this reaction exists in equilibrium. So that's what I wanted to talk about. I'm not going to color coordinate this because I'm not really talking about that. But let's compare the pKa values to understand why that we've specifically drawn this reaction in equilibrium as opposed to the other one. So the pKa value of a hydronium ion, H3O plus in water, is about, and this is an approximation, I should clarify that that's an approximation, -1.7. This is straight from what my textbook gives me. And then the pKa values for a protonated ketone, though, has a pKa value of approximately, again, -7. So pretty large difference between the two. But if you notice that one of the things that we often, a rule of thumb to go by in understanding this reaction is that anytime the difference is between your two pKa values, so I'm just going to say that here's the difference. So if your pKa difference is less than or equal to 10 orders of magnitude, so I'm just going to say 10 magnitude, then obviously anytime this is the case, you're going to get an equilibrating reaction. This reaction is going to be equilibrating. Obviously with a pKa of -7, it's going to want to really favor the reverse reaction. But because of Les Chataliers' principle, which is a general chemistry concept, and I'm going to make the assumption that you know how that works already, if we add more add more starting materials to our reaction, it's going to go in the forward direction. Now, just at the very end, just this is a fun fact here, note that this hydronium ion is acting as a catalyst. Catalysts, and at the end of the reaction, we're going to form hydronium ion. Catalysts are not destroyed in reactions. They always exist. And so this kind of makes it kind of frustrating, and a lot of students overthink and get lost. But if you're ever wondering, well, is this an equilibrating reaction or is this going in a forward direction, the differences in your pKa values, that's going to give you information on whether or not that's the case. Now with acetals, one of the things that obviously for Les Chataliers' principle, we can simply add more of our reactants, or we can remove a product if we want our reaction to go forward. So one of the things that we can do with acetals that we really can't do, I guess, with hydrate formation so much, I don't know why I listed two things there, it's really just one or two things, not three, but the things that we can do to remove our product. So obviously we can put this under highly acidic conditions to explain this, but we can treat this with anything that's going to be a dehydrating agent. That's going to be removing the water from our reaction, which that water is going to interact with the acid that we have. That's bad, but also that water is the leaving group that we may or may not be forming depending on the nature of your reaction. So we treat this as a dehydrating agent in something called a Dean-Stark apparatus. I'm just going to say DS-app. Dean-Stark apparatus, and I'd love to talk about that, but that's something more or less that you learn for lab. But what are we doing here? We're removing the product, and that's how we can apply Les Chataliers' principle.